Parker Solar Probe had been watching the Sun's corona for 7 years, its whisper camera capturing the violent dance of solar winds and magnetic field lines with mechanical precision. On October 28, 2025, at 3:47 Coordinated Universal Time, something appeared in frame 17,212 that had nothing to do with the Sun. The detection happened during a routine perihelion pass, that closest approach where the probe skims just 4 million miles above the solar surface. At these distances, the spacecraft operates on autopilot, its cameras programmed to capture images at predetermined intervals, while mission controllers on Earth wait for the data download hours later. The images arrive in batches, processed through algorithms designed to filter cosmic ray hits, instrument noise, and other artifacts that plague deep space photography. Frame 17,212 showed 3I Atlas exactly where orbital predictions placed it, a faint smudge against the star field backdrop, its coma barely visible in the extreme ultraviolet wavelengths whisper monitors. The object had been tracked continuously since its discovery 5 months earlier, its trajectory mapped with increasing precision by observatories worldwide. Nothing about its appearance suggested anything unusual. Frame 17,213 changed everything. Approximately 0.15 astronomical units behind 3I Atlas, roughly 14 million miles in its wake, another object appeared. The signature was faint, nearly lost in the background noise, but the image processing algorithms flagged it immediately. Elongated, darker than the surrounding space, moving through the frame at a rate consistent with solar system escape velocity. The initial assumption among mission controllers at Johns Hopkins Applied Physics Laboratory was straightforward: cosmic ray hit. These high-energy particles from deep space constantly bombard spacecraft instruments, creating false signals that experienced analysts learn to recognize and dismiss. But cosmic ray artifacts appear as single-pixel anomalies, brief flashes that vanish in subsequent frames. Frame 17,214 showed the object again, slightly displaced from its previous position, moving in a trajectory that matched 3I Atlas with unsettling precision. 4 hours passed before the full image sequence reached Earth. Another 3 hours elapsed as mission specialists reviewed the data, cross-referenced orbital mechanics calculations, and ran diagnostic checks on the camera systems. By hour 7, the conclusion became unavoidable. This was not an artifact. This was not a known asteroid or comet. This was something new, something large, and something that had apparently been following humanity's third confirmed interstellar visitor through the inner solar system without anyone noticing. The emergency protocols activated at hour 8. NASA's Center for Near-Earth Object Studies received the preliminary trajectory data. The European Space Agency's Space Situational Awareness Center joined the conference call minutes later. The Minor Planet Center prepared to issue alerts to the global observatory network. And somewhere in a secured communication room, someone made the decision that would shape everything that followed. For the next 72 hours, the discovery would remain classified, while confirmation observations determined whether humanity had just detected its 4th interstellar visitor, or something far stranger. Within 4 hours of Parker Solar Probe's detection, the global astronomical community mobilized with unprecedented speed. The emergency protocol, established after the Oumuamua controversy, when coordination failures delayed critical observations, transformed a routine discovery pipeline into something resembling a military operation. This was no longer about academic curiosity. This was about capturing data on an object that might disappear beyond observational reach within weeks. NASA's Center for Near-Earth Object Studies became the coordination hub, processing the preliminary trajectory data from Parker Solar Probe, while simultaneously tasking every available space-based asset toward the target coordinates. The European Space Agency's Space Situational Awareness Center joined within minutes, their parallel tracking systems providing independent confirmation that reduced the possibility of instrumental error to near zero. The Minor Planet Center, responsible for cataloging all solar system objects, prepared emergency bulletins for the global observatory network. The protocol mandated specific priorities. First, confirmation through multiple independent observations. Second, rapid trajectory determination to establish whether the object posed any collision risk to Earth or spacecraft. Third, preliminary characterization through spectroscopy and photometry. Fourth, and only after completing the first 3 steps, public announcement. Ground-based observatories across 6 continents received encrypted alerts at hour 4. The message contained precise coordinates, predicted motion vectors, and urgency codes that superseded all existing observation schedules. Facilities in Chile pivoted their massive mirrors skyward as local sunset provided viewing opportunities. Australian observatories prepared for their own darkness hours ahead. European facilities calculated optimal observation windows for the coming night. Hubble Space Telescope mission controllers received a director's discretionary time request, the rarest category of observing proposal, reserved for time-critical discoveries. The approval process that normally requires weeks compressed into 40 minutes. Someone at the Space Telescope Science Institute recognized that missing this opportunity meant potentially losing the object forever as it accelerated toward the outer solar system alongside 3I Atlas. The James Webb Space Telescope faced more complex scheduling challenges. Its deep space position at the second Lagrange point meant any target of opportunity observation required careful thermal management to prevent sunlight from damaging its sensitive infrared instruments. Mission planners worked through orbital geometry calculations, determining the earliest safe observation window, while the object remained within Webb's operational constraints. The media blackout proved more difficult to maintain than anyone anticipated. Amateur astronomers monitoring public observation schedules noticed the sudden coordination, the simultaneous telescope pointings toward the same region of sky. Social media speculation began within 8 hours, forcing space agencies to accelerate their confirmation timeline. By hour 16, the decision was made: announce early or lose control of the narrative entirely. The provisional designation came first, 4I/2025U1, indicating the 4th confirmed interstellar object and its discovery date in late October. The name would stick even after formal classification, much like 3I Atlas had become the common designation for its predecessor. But names mattered less than the fundamental question now dominating every emergency planning session. Why was something significantly larger than 3I Atlas following it through our solar system with trajectory precision that defied conventional orbital mechanics? The confirmation cascade began 36 hours after Parker Solar Probe's initial detection, when Hubble Space Telescope completed its first observation run of 4I/2025U1. The images arrived at the Space Telescope Science Institute as raw data streams, pixels representing photons that had traveled millions of miles from an object whose very existence challenged astronomical expectations. What those pixels revealed made the emergency protocol feel inadequate. The object was real, not an instrumental artifact, not a data processing error, not cosmic ray contamination. A solid body moving through space with measurable position, apparent brightness, and trajectory that could be calculated with increasing precision. Hubble's wide-field camera 3 captured the object as a distinct point source against the stellar background, its motion between successive exposures confirming the preliminary orbital solution derived from Parker's initial detection. Size estimates from photometric data suggested something between 15 and 20 kilometers in diameter, making it substantially larger than 3I Atlas. The brightness measurements, combined with distance calculations, allowed astronomers to estimate albedo, that fraction of sunlight the object reflects back into space. The number that emerged from these calculations shocked the observation teams: 0.03 to 0.05, darker than coal, darker than the blackest carbonaceous asteroids known in the solar system, darker than almost anything ever observed in nature. James Webb Space Telescope's observations followed 20 hours later, its infrared sensors probing wavelengths invisible to human eyes and most ground-based instruments. The near-infrared spectrograph revealed what Hubble could not see: the thermal signature. Objects in space absorb sunlight and re-radiate that energy as heat, creating predictable temperature patterns based on distance from the Sun and surface composition. 4I-2025. U1 radiated at temperatures 40 degrees, Kelvin below what physics predicted for its heliocentric distance. Ground-based observatories contributed their own confirmations throughout the following week. The European Southern Observatory's Very Large Telescope in Chile captured spectroscopic data showing virtually no emission lines. No water vapor, no carbon dioxide, no cyanogen, none of the volatile compounds that create the characteristic signatures of active comets. The object appeared chemically inert, a dark boulder drifting through the void without the gas and dust production that made 3I Atlas so visually striking. Gemini North Observatory in Hawaii attempted polarimetry observations to characterize surface properties. The reflected sunlight showed unusual polarization patterns inconsistent with natural regolith, the pulverized rock dust that typically covers asteroid surfaces. The patterns suggested something about the surface structure that required additional observations to interpret properly. Each new dataset refined the trajectory solution, and that trajectory told perhaps the most unsettling story of all. 4I-2025. U1 was not just travelling through the solar system on a hyperbolic path, similar to 3I Atlas. It was following 3I Atlas with precision that orbital mechanics alone could not easily explain. The inclination matched within 0.02 of 1 degree. The velocity differential remained below 2 kilometers per second. Two objects, both interstellar, moving in formation through our cosmic neighborhood as though connected by invisible threads. The first comprehensive spectroscopic analysis of 4I-2025 U1 revealed something that made no sense in the context of everything astronomers understood about comets, asteroids, and interstellar objects. The spectrum was almost completely featureless. Where 3I Atlas had blazed with emission lines from water vapor, carbon dioxide and exotic organic compounds. Its companion showed virtually nothing. Spectroscopy works by splitting light into its component wavelengths, revealing the chemical fingerprints of elements and molecules. Every substance absorbs or emits light at characteristic frequencies, creating patterns as distinctive as human fingerprints. When sunlight reflects off a comet or asteroid, that reflected light carries information about surface composition. When gas sublimates from a warming nucleus, those gases emit light at specific wavelengths that instruments can detect and measure. 4I 2025. U1 defied these expectations. The reflected sunlight showed only a featureless continuum, a smooth curve devoid of the absorption features that typically indicate surface minerals, ices, or organic compounds. The lack of emission lines meant no detectable outgassing, no sublimating ices, no active chemistry responding to solar heating. For an object at its current distance from the Sun, this absence made it fundamentally different from 3I Atlas, which had been actively producing gas and dust throughout its entire passage through the inner solar system. The albedo measurements compounded the mystery. An albedo of 0.03 means the object reflects only 3% of incident sunlight, absorbing the remaining 97%. For comparison, fresh asphalt reflects about 7% of sunlight. Charcoal reflects roughly 4%. The darkest known asteroids, carbonaceous chondrites, rich in organic compounds and water-bearing minerals, typically reflect between 3 and 9%. 4I 2025. U1 sat at the extreme lower end of this range, darker than almost any natural surface ever measured. Temperature readings added another layer of strangeness. Infrared observations from James Webb Space Telescope and ground-based facilities measured the object's thermal emission, the heat it radiates back into space after absorbing sunlight. The temperature came in 40 degrees, Kelvin colder than predictions based on its distance from the Sun and its measured albedo. Physics demanded an explanation. Objects absorb sunlight and warm up according to well-understood thermodynamic principles. Finding something colder than it should be meant either the measurements were wrong or something about the object's properties violated standard assumptions. Several hypotheses emerged to explain the spectral silence. Perhaps the surface consisted of materials with unusually low reflectance across all wavelengths, some exotic combination of carbon compounds and metallic elements that absorbed light without creating distinctive spectral features. Perhaps a thick layer of dust or regolith masked whatever composition lay beneath, smoothing out characteristic absorption patterns. Perhaps the object was simply too cold, too distant, or too inactive to produce detectable emission signatures. But none of these explanations addressed the central paradox. Why would two interstellar objects, traveling in precise formation through our solar system, exhibit such radically different behaviors? 3I Atlas actively sublimated volatiles and produced visible coma structures. 4I 2025. U1 remained silent, dark, and inert. The contrast suggested they formed in different environments, experienced different histories, or consisted of fundamentally different materials. Yet their trajectories implied connection, coordination, purpose. Determining the actual size of 4I 2025 U1 became one of the most contentious debates in modern astronomy. The photometric data, those brightness measurements collected by telescopes worldwide, provided only indirect size estimates that depended critically on assumptions about the object's reflectivity and shape. With an albedo hovering near 0.03, uncertainties in that single parameter translated into massive uncertainties in calculated diameter. The basic physics is straightforward. An object's brightness depends on three factors: its size, its distance, and how much light it reflects. Astronomers can measure brightness directly and calculate distance from orbital mechanics. But reflectivity remains unknown until you either visit the object directly or make careful observations across multiple wavelengths and viewing geometries. With 4I-2025-U1, those observations yielded confusing results. Initial estimates placed the diameter between 15 and 20 kilometers, making it roughly 3 to 4 times larger than 3I Atlas in linear dimensions, but volume scales with the cube of diameter. If 4I-2025-U1 truly measured 20 kilometers across, it could contain 64 times more material than its 5-kilometer companion. Using typical comet densities, around 500 kilograms per cubic meter, that translated to potential masses exceeding 2 trillion tons, thousands of times heavier than 3I Atlas. The problem was that these calculations assumed the object was roughly spherical. Elongated shapes change everything. Oumuamua's controversial cigar-like proportions had demonstrated how shape assumptions could lead astronomers astray. If 4I-2025-U1 was highly elongated, stretching perhaps 50 kilometers in one dimension, while measuring only 5 in others, the mass estimates would need complete revision downward. Occultation observations offered one path toward resolving the size controversy. When an asteroid or comet passes in front of a distant star, ground-based observers can time precisely when the starlight disappears and reappears, using those measurements to determine the object's profile. But occultations require perfect geometric alignment between the object, background star, and Earth-based observers. The prediction calculations for 4I-2025-U1 showed no favorable occultation opportunities for at least 8 months. Radar observations provided another potential measurement technique. The Arecibo Observatory's successor facilities in the continental United States attempted ranging experiments, bouncing radio waves off the object's surface to measure size and rotation directly. The returns were weak but detectable, suggesting a surface composition that absorbed radio frequencies even more efficiently than visible light. The radar cross-section data, still being analyzed by multiple research teams, hinted at diameters in the 18 to 22 kilometer range, but with error bars spanning several kilometers in either direction. Mass remained completely unconstrained without observations of non-gravitational acceleration. Unlike 3I Atlas, which showed measurable orbital deviations from outgassing forces that allowed mass estimation, 4I-2025-U1 followed a purely gravitational trajectory. No jets, no thrust, no measurable forces beyond solar gravity and radiation pressure. Without those tiny accelerations to reveal how massive the object truly was, astronomers could only guess at its bulk properties. And those guesses ranged across 3 orders of magnitude, from hundreds of billions of tons to over 1 trillion tons of silent, dark material drifting through our solar system in formation with its active companion. The orbital mechanics of 4I-2025-U1 defied conventional explanation through natural processes. Astrometry teams across the globe had accumulated enough positional measurements to calculate the object's trajectory with extraordinary precision. And that trajectory told a story that made gravitational dynamics experts deeply uncomfortable. The inclination matched 3I Atlas to within 0.02 of 1 degree. To understand how remarkable this alignment was, consider that objects entering the solar system from interstellar space can arrive from any direction in 3-dimensional space. Random arrivals should show inclinations distributed across all possible angles relative to the planetary plane. The probability of 2 independent interstellar objects arriving with inclinations, this similar approaches 1 in several thousand. But the trajectory coincidences extended far beyond inclination. The velocity differential between the 2 objects measured less than 2 kilometers per second. Both were traveling on hyperbolic escape trajectories, moving fast enough to eventually leave the solar system entirely. But their speeds matched with precision that seemed impossible for objects that presumably originated in different stellar systems, perhaps light years apart. The separation distance added another layer to the puzzle. 4I 2025. U1 trailed 3I Atlas by approximately 0.15 astronomical units, roughly 14 million miles. This distance was slowly decreasing as both objects continued their journey through the inner solar system. Orbital calculations projected closest approach in February 2026, when the separation would shrink to 0.08 astronomical units, about 12 million kilometers. Gravitational binding between the objects could explain formation flight if they were orbiting each other, like binary asteroids or contact binaries common in the solar system. But the calculated gravitational force between 2 objects of their estimated masses at 14 million mile separation was negligible, far too weak to maintain any orbital relationship. They were not gravitationally bound, yet they were traveling together with coordination that gravity alone could not produce. The trajectory also showed both objects would pass within relatively close range of Jupiter in March 2026. The gas giant's massive gravitational field would alter both trajectories, but preliminary calculations suggested the deflections would maintain their relative positioning. Somehow, the objects would emerge from the Jupiter encounter still traveling in formation, still separated by manageable distances, still coordinated in ways that frustrated attempts at natural explanation. Several research groups attempted to model scenarios where tidal forces during a close stellar encounter could launch multiple objects on similar trajectories. The physics worked in principle. If both objects originated in the same stellar system and were ejected during the same dynamical event, they might retain similar velocities and inclinations. But even these models struggled to explain the precision of the observed alignment. The velocity matching was particularly problematic. Objects ejected from planetary systems typically gain random velocity kicks from gravitational scattering events. Those kicks should produce velocity spreads of tens or hundreds of kilometers per second between different ejecta. Finding 2 objects with velocity differential below 2 kilometers per second suggested either incredibly specific ejection geometry or some mechanism actively maintaining their formation configuration. Neither explanation fit comfortably within conventional astrophysics. The trajectory data was forcing astronomers toward uncomfortable conclusions about what they were actually observing. The binary breakup theory emerged as the first serious attempt to explain how 2 interstellar objects could be traveling together through our solar system. The hypothesis drew on decades of comet observation, showing that fragmentation events, while dramatic, follow well-understood physical principles. If 3I Atlas and 4I 2025 U1 had once been a single object that broke apart before or during solar system entry, their coordinated trajectories would make perfect sense. Historical precedent supported the basic concept. Comet Shoemaker-Levy 9 remains the most famous fragmentation example, torn into more than 20 pieces by Jupiter's tidal forces in 1992, before those fragments crashed into the gas giant 2 years later. The event demonstrated that gravitationally bound objects could survive breakup while maintaining similar trajectories for extended periods. Ground-based observatories had documented dozens of similar splitting events in solar system comets, usually triggered by thermal stress, rotation, or tidal forces during close approaches to the Sun or planets. The mathematics of binary breakup provided testable predictions. If the two objects separated from a common parent body, the event would have imparted relative velocity between the fragments. That separation velocity, combined with time since breakup, determines current spacing, working backwards from the observed 14 million mile separation and 2 km/s velocity differential. Researchers calculated that breakup must have occurred roughly 8 to 10 months before Parker Solar Probe's detection. Timeline reconstruction suggested the separation happened before solar system entry, somewhere in interstellar space as the parent object approached our stellar neighborhood. Several mechanisms could trigger such a breakup. Thermal stress from increasing solar heating as the object fell toward the inner solar system could crack weakly bound contact binaries. Rotational instability could spin apart objects held together by minimal gravitational or tensile forces. Tidal stress from passing near the Sun or planets could physically tear apart bodies with insufficient internal strength. But the binary breakup theory faced a critical observational challenge. Fragmentation events create debris fields. When comets split, they leave trails of smaller fragments, dust, and gas along their orbital paths. Shoemaker-Levy 9's fragment chain was visible for 2 years before impact. Solar system comet splitting events produce spectacular dust tails, marking the separation location. Astronomical surveys monitoring the space between 3I Atlas and 4I 2025 U1 found nothing. No intermediate-sized fragments, no dust clouds, no evidence of the violent separation that must have occurred. The chemical composition mismatch presented another problem for the hypothesis. 3I Atlas blazed with water vapor, carbon dioxide, and complex organic emissions. 4I 2025 U1 showed spectral silence, no volatiles, no activity, no chemical signatures matching its supposed sibling. If both objects originated from a common parent body, they should share similar compositions, unless the breakup somehow exposed radically different internal layers with distinct chemistry. The size ratio also troubled some researchers. Breaking a single object into one 5-kilometer piece and one 20-kilometer piece seemed backwards. Fragmentation typically produces one large remnant and many smaller pieces, not a smaller active body accompanied by a larger inert one. The physics of how such asymmetric breakup could occur required special pleading about internal structure and breakup geometry that felt increasingly contrived as more data accumulated. Contact binaries offered a more refined version of the breakup hypothesis. one that drew on detailed observations of solar system comets, showing that many form as gentle mergers of smaller objects, rather than single monolithic bodies. Comet 67, P. Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta mission in 2014, provided the template for this alternative explanation. Its distinctive rubber duck shape resulted from two separate lobes joined at a narrow neck, demonstrating that comets could maintain dual component structures over billions of years. The contact binary scenario proposed that 3I Atlas and 4I 2025 U1 began their interstellar journey as a single loosely bound system, two objects in gentle contact or very close orbit around each other. As this binary approached the Sun, thermal stress from solar heating could have weakened the connection between components. Differential heating, where one side facing the Sun warms faster than shadowed regions, creates mechanical stress that can break apart weakly bound structures. This mechanism had been observed in solar system comets. Comet 73, P. Schwassmann-Wachmann. 3 fragmented into multiple pieces during its 26th apparition, splitting along pre-existing structural weaknesses as solar heating cycled the nucleus through temperature extremes. Comet 16, P. Brooks. 2 showed similar behavior, separating into components that then followed nearly identical orbits for years. The gentle separation process in contact binary breakup would explain the absence of a debris field. Rather than a violent explosion or catastrophic tidal disruption, the components would simply drift apart at low relative velocity, perhaps less than a few meters per second initially. Over months of continued separation, that minimal velocity differential would accumulate into the millions of miles now separating the objects. Rotational dynamics could enhance this separation mechanism. Many comets spin rapidly, their rotation rates determined by the gravitational scattering events that ejected them from their parent stellar systems. As a rotating contact binary approaches the Sun, outgassing from the active component creates jets that act like rocket thrusters. These jets can either spin up or slow down the rotation depending on their orientation. If asymmetric outgassing increased rotation past the critical threshold, where centrifugal forces exceeded the weak gravitational binding between components, the binary would fly apart. But the contact binary alternative faced the same chemical composition problem that plagued the simpler breakup theory. If 3I Atlas and 4I 2025 U1 were once joined in a contact binary configuration, their surface compositions should show similarities. Instead, spectroscopic observations revealed radical differences. One object actively sublimated volatiles rich in carbon dioxide and water. The other showed no volatile signatures whatsoever, just dark, inert material absorbing sunlight without chemical response. The size ratio remained problematic as well. Contact binaries typically form from comparable-sized components. Finding a 5-kilometer active component joined to a 20-kilometer inactive component required explaining how such asymmetric binaries could form and survive. The gravitational dynamics of maintaining contact between such disparate masses created additional theoretical challenges. Most troubling was the timing. If thermal stress triggered separation, the event should have occurred during closest approach to the Sun, when heating reached maximum intensity. But both objects were still approaching perihelion when Parker Solar Probe detected them already separated by 14 million miles. The separation must have happened much earlier, perhaps before entering the inner solar system, when solar heating remained minimal and insufficient to break apart even weakly bound structures. The statistical improbability of two independent interstellar objects traveling together forced astronomers to confront what became known as the escort paradox. The numbers were unforgiving, even if breakup theories proved incorrect and the objects had always been separate. The precision of their trajectory matching exceeded what random chance could produce by factors that made conventional explanations seem increasingly inadequate. Start with the basics of interstellar object arrival statistics. Objects entering the solar system from the vast spaces between stars can approach from essentially any direction in three-dimensional space. Their velocities depend on the galactic orbital motions of their parent stellar systems, plus whatever ejection velocities launch them into interstellar space. These factors combine to produce a wide distribution of possible arrival trajectories, inclinations, and speeds. The probability that two independent objects would arrive with inclinations matching to within 0.02 degrees calculates to roughly 1 in 5,000. Add the requirement that their velocities differ by less than 2 kilometers per second, and the probability drops to approximately 1 in 50,000. Include the coincidence that both objects arrive within months of each other, rather than being separated by years or decades, and the combined probability falls below 1 in 10 million. These aren't abstract theoretical concerns. They represent fundamental questions about whether the observations could result from chance alone, or require some physical mechanism maintaining the formation configuration. When probabilities drop below 1 in a million, scientists start looking very carefully for systematic explanations, rather than accepting cosmic coincidence. Gravitational capture scenarios offered one potential systematic explanation. Perhaps 4i 2025 U1 was originally traveling on a different trajectory and got gravitationally captured into formation with 3i Atlas through a complex multi-body interaction involving the Sun or planets. The problem was that such captures require very specific geometric conditions and energy dissipation mechanisms. Objects don't simply slide into formation with each other through gravity alone. They need something to remove kinetic energy, like atmospheric drag for satellites around Earth, or gas drag in protoplanetary disks around young stars. The near vacuum of interplanetary space provides no such mechanism. Three-body interactions involving the Sun could theoretically place two objects on similar trajectories, but the calculations required implausibly precise initial conditions. The objects would need to arrive from different directions at exactly the right times, with exactly the right velocities, to emerge from their solar encounters on matched hyperbolic orbits. Running the probabilities through orbital dynamics simulations produced scenarios that worked mathematically, but seemed absurdly contrived physically. The escort paradox became even more acute when considering observational selection effects. Survey telescopes naturally bias toward detecting objects near the ecliptic plane where most asteroids and comets reside. This geometric bias might explain finding one ecliptic-aligned interstellar visitor, but finding two traveling together pushed beyond what selection effects could reasonably explain. The coordination itself was the observation, not an artifact of how astronomers search the sky. Some researchers began suggesting that the trajectory matching wasn't coincidental at all, but represented active maintenance of formation configuration. This interpretation implied either unknown physics operating between the objects or controlled propulsion systems aboard one or both bodies. Neither possibility fit comfortably within conventional astronomy, but the alternative required accepting coincidences that violated statistical common sense. The escort paradox was forcing the field toward conclusions that most astronomers found deeply uncomfortable. James Webb Space Telescope's near-infrared spectrograph, observations of 4I-2025, U1 revealed chemical signatures that deepened the mystery rather than resolving it, while 3I Atlas displayed the volatile rich composition expected of comets formed in cold stellar environments. Its companion showed something entirely different. Complex organic molecules, specifically polycyclic aromatic hydrocarbons, dominated the spectral features in ways that had never been seen in any solar system, comet or asteroid. Polycyclic aromatic hydrocarbons, commonly abbreviated as PAHs, are carbon-based molecules consisting of multiple fused benzene rings. These compounds form in carbon-rich environments and appear throughout the universe, detected in interstellar clouds, protoplanetary disks, and the atmospheres of some planets. But finding them concentrated on the surface of what appeared to be an interstellar boulder raised immediate questions about formation conditions and chemical processing. The detection came through characteristic infrared emission features at wavelengths of 3.3, 6.2, 7.7, 8.6, and 11.3 micrometers. These spectral signatures resulted from carbon-hydrogen and carbon-carbon bond vibrations within the PAH molecular structures. The strength of these features suggested PAH concentrations far exceeding anything observed in solar system objects, where such molecules typically appear only as trace contaminants mixed with silicate minerals and water ice. Even more puzzling was what the spectra didn't show. Nitrogen compounds, abundant in 3I Atlas and common in comets generally, were conspicuously absent from 4I 2025 U1's spectral signature. Water ice absorption, features that appear prominently in most outer solar system objects, registered below detection limits. The surface appeared to be dominated by carbon compounds to the near exclusion of the oxygen-rich and nitrogen-rich materials that typically constitute cometary nuclei. This chemical dichotomy between the two objects challenged any remaining versions of the common origin hypothesis. If they formed together in the same stellar environment, experienced the same thermal and radiation processing, and travelled through interstellar space under similar conditions, their compositions should show at least broad similarities. Instead, they appeared as chemically distinct as Earth and Mars, suggesting formation in radically different environments or exposure to very different processing histories. Radar observations from upgraded Arecibo successor facilities provided complementary information about subsurface composition. The radar reflection characteristics, specifically the polarization ratios of returned signals, indicated a surface rich in metallic or highly conductive materials, mixed with the organic compounds. Natural carbonaceous asteroids show some radar reflectivity from embedded metal grains, but 4I 2025 U1's returns suggested metal concentrations exceeding typical meteoritic abundances. The metal-rich composition inference gained support from the object's unusually low temperature. Metals conduct heat efficiently, allowing thermal energy to spread throughout a body rather than concentrating near the sun-facing surface. A metal-rich interior could could explain why 4I-2025 U1 radiated at temperatures 40 degrees Kelvin below predictions, its internal thermal conductivity redistributing absorbed solar energy more efficiently than typical rocky or icy materials. The combination of concentrated organic compounds and metallic elements created a compositional profile without clear analogues in solar system experience. Some researchers noted similarities to certain classes of meteorites, particularly those showing evidence of aqueous alteration in parent body interiors. But even the most chemically processed meteorites showed nothing like the extreme PAH concentrations and metal enrichment evident in 4I-2025 U1's observational signatures. Polarimetry observations revealed something that pushed 4I-2025 U1's strangeness into entirely new territory. The technique measures how light's electromagnetic waves orient themselves after reflecting from surfaces, providing information about surface texture, composition, and geometric structure that standard photometry cannot detect. What polarimetry showed about the object's surface challenged natural geological explanations. Natural surfaces scatter light in patterns determined by particle size, surface roughness, and viewing geometry. Rocky asteroids produce predictable polarization signatures as sunlight bounces off irregular mineral grains and impact pulverized regolith. Icy surfaces create different patterns due to crystalline structure and transparency. Decades of solar system observations had established empirical relationships between polarization measurements and surface properties, relationships that worked reliably for thousands of objects. 4I-2025 U1 violated these relationships. Observations across multiple wavelengths and viewing angles showed polarization variations that didn't match any known natural surface type. The patterns suggested non-random structure at scales ranging from micrometers to meters, geometric organization that natural weathering processes don't typically produce. The anomaly appeared most prominently at specific wavelengths in the near infrared. At these frequencies, the reflected light showed polarization degrees significantly higher than expected for randomly oriented surface materials. The effect resembled what engineers observe when measuring light reflection from manufactured surfaces, with microscopic structures designed to control optical properties. Surfaces like diffraction gratings or photonic crystals engineered for specific technological applications. Radar observations from multiple facilities corroborated the polarimetry findings through independent measurement techniques. Radar reflections carry polarization information determined by surface electrical properties and geometric structure. Natural rocky surfaces depolarize radar signals through multiple scattering from irregular features. Smooth surfaces or aligned structures preserve polarization, creating distinctive signatures. 4I-2025 U1's radar returns showed partial polarization preservation inconsistent with natural regolith. The polarization ratios suggested surface regions with preferred orientations or periodic structures at centimeter to meter scales. Some radar echoes showed what appeared to be specular reflection, mirror-like bouncing that requires unusually smooth surfaces or geometric faceting, rather than the diffuse scattering typical of asteroid surfaces. Comparison with metallic asteroids offered potential natural analogues. The handful of known metal-rich asteroids, presumably exposed iron-nickel cores of differentiated planetesimals shattered by ancient collisions, show somewhat unusual reflectance, properties due to their composition. But even these objects display radar and polarimetry signatures consistent with impact-battered, regolith-covered surfaces. Their reflectance remains fundamentally random at small scales, despite bulk metallic composition. The geometric patterns in 4I-2025 U1's reflectance suggested structure, organization, something more than random arrangement of surface materials. Statistical analysis of the polarimetry data showed correlations between measurements at different wavelengths and viewing angles that natural surfaces don't typically produce. The patterns weren't dramatic enough to prove artificial origin, but they were consistent enough to make geologists uncomfortable. Several research teams attempted to model natural formation scenarios that could produce the observed reflectance anomalies. Proposals included unusual crystallization patterns during slow cooling of metallic melts, tidal stress creating aligned fracture networks, or preferential erosion by interstellar dust impacts over millions of years, creating micro-scale geometric features. Each model could explain isolated aspects of the observations, but struggled to account for the full suite of polarimetry and radar measurements simultaneously. The reflectance anomaly joined the growing list of characteristics that individually might accept conventional explanation, but collectively painted a picture that didn't fit comfortably within natural object categories. Every new observation seemed to deepen rather than resolve the fundamental question of what 4I-2025 U1 actually was. The thermal anomaly detected by infrared observatories became impossible to dismiss as measurement error after multiple independent facilities confirmed the same peculiar result. 4I-2025 U1 radiated heat at levels that exceeded what solar absorption alone could explain. The excess wasn't dramatic, not the blazing infrared signature of a recently formed body still glowing from accretion heat. But it was persistent, measurable, and physically significant. Infrared astronomy works by detecting the heat that objects emit as thermal radiation. Every object above absolute zero radiates electromagnetic energy according to its temperature, with hotter objects emitting more total energy and shifting that emission toward shorter wavelengths. By measuring the infrared brightness across multiple wavelengths, astronomers can determine surface temperatures and, with careful modeling, infer properties about internal heat sources. 4I-2025 U1's temperature measurements showed consistent excess across the infrared spectrum. The object was roughly 15 to 20 degrees, Kelvin warmer than predictions based on solar heating at its current distance from the Sun. This might not sound significant, but at the low temperatures characteristic of outer solar system objects, a 20-degree excess represents substantial energy flux requiring explanation. Solar heating provides the dominant heat source for most solar system bodies. Objects absorb sunlight, warm up until they reach equilibrium temperatures, where absorbed energy equals radiated energy, then maintain those temperatures as long as solar flux remains constant. The equilibrium temperature depends on distance from the Sun, albedo, and thermal properties like conductivity and heat capacity. For 4I-2025, U1's measured albedo and heliocentric distance, equilibrium calculations predicted temperatures around 130 degrees Kelvin. Observations consistently measured 145 to 150 degrees. Several natural heat sources could theoretically explain the excess. Radioactive decay of unstable isotopes produces heat in planetary interiors, the same process that keeps Earth's core molten billions of years after formation. But achieving measurable surface temperature increases from radioactive heating requires either very high concentrations of radioactive elements or very small object sizes that minimize the insulating effect of overlying material. 4. I-2025. U-1's estimated 20-kilometer diameter made radioactive heating an unlikely explanation, unless it contained uranium or thorium concentrations, far exceeding any known meteoritic composition. Tidal heating offered another potential mechanism. When objects orbit close to massive bodies, gravitational gradients create internal friction that generates heat. Jupiter's moon Io demonstrates this effect dramatically, its surface melting from tidal flexing despite its distance from the Sun. But 4 I-2025 U-1 wasn't orbiting anything. It followed a hyperbolic escape trajectory with no close approaches to planets or the Sun that could produce significant tidal stress. Recent collision energy represented a third possibility. If the object had experienced a major impact in the relatively recent past, perhaps during ejection from its parent stellar system or during interstellar transit, the kinetic energy converted to heat during impact could still be radiating away. The thermal relaxation time, how long it takes for an object to cool back to equilibrium after heating, scales with size. A 20-kilometer body could retain impact heat for thousands or millions of years, depending on thermal conductivity. But impact heating faced a timing problem. The probability that humanity would detect an interstellar object during the brief period when it still retained measurable impact. Heat seemed vanishingly small unless such events were far more common than current models suggested. The scientific establishment rallied around natural explanations with determination that reflected both genuine conviction and institutional conservatism. Mainstream astronomers, planetary scientists, and dynamicists argued forcefully that the unusual characteristics of 4 I-2025 U-1, while intriguing, fell within the range of phenomena that natural processes could produce. Extraordinary claims required extraordinary evidence, and nothing yet observed definitively ruled out conventional astrophysics. The carbonaceous interstellar boulder scenario gained traction as the leading natural explanation. This framework proposed that 4 I-2025 U-1 represented an exceptionally large fragment of carbon-rich material, perhaps a chunk of primordial nebula material that never fully incorporated into a planet or underwent significant thermal processing. Such objects would be naturally dark, rich in organic compounds, including polycyclic aromatic hydrocarbons, and potentially enriched in metallic elements that condensed alongside carbon in stellar outflows. Carbonaceous chondrite meteorites provided terrestrial analogues for this composition. These primitive meteorites contain high concentrations of organic compounds, water-bearing minerals, and metallic grains mixed in a carbon-rich matrix. Some carbonaceous chondrites show albedos as low as 0.03, matching 4 I-2025 U-1's measured reflectance. The spectral signatures, while unusual, weren't impossible for highly processed carbonaceous material exposed to millions of years of cosmic ray bombardment and interstellar radiation. The thermal excess received attention from researchers modeling residual heat scenarios. Several papers calculated that a collision occurring within the past million years could leave a 20-kilometer object with detectable temperature elevation. The interstellar environment isn't completely empty. Occasional collisions with smaller debris during multi-million-year journeys between stellar systems seemed statistically plausible. One significant impact could explain both the thermal signature and potentially some of the surface structure anomalies detected by polarimetry and radar. The trajectory coordination with 3I Atlas posed the biggest challenge for natural explanations, but the coalition focused on selection effects and coincidence timing. Survey geometries strongly biased detection toward objects near the ecliptic plane. Perhaps the apparent coordination reflected observational selection rather than physical connection. The universe contains billions of interstellar objects. Finding two traveling on similar trajectories might seem improbable for any specific pair. But given enough objects wandering through the galaxy, occasional close passages become inevitable. Ejection from a common stellar system offered the most physically motivated explanation for trajectory similarity. If both objects originated in the same planetary system and were ejected during the same dynamical event, perhaps a stellar encounter or planetary migration episode, they could retain similar velocities and inclinations for millions of years. The chemical differences could reflect formation at different distances from their parent star, with 3I Atlas originating in volatile-rich outer regions, while 4I 2025 U1 formed closer in, where only refractory materials condensed. The lack of debris field between objects didn't necessarily rule out common origin, the coalition argued. If separation occurred millions of years ago in interstellar space, any debris would have dispersed beyond detection limits. The precision of current trajectory matching could result from both objects experiencing similar gravitational perturbations during their journey through the galaxy. Periodic interactions with molecular clouds or stellar encounters that nudged both trajectories in parallel directions. The natural coalition emphasized scientific methodology over speculation. Publish peer-reviewed analyses, wait for more data, avoid premature conclusions about exotic phenomena. Every historical anomaly in astronomy, from pulsars to gamma-ray bursts, eventually received natural explanations once sufficient observations accumulated. 4I 2025 U1 would follow the same pattern. The technological interpretation found its most articulate advocates among researchers who had spent years analyzing Oumuamua's anomalies and developing statistical frameworks for distinguishing natural from artificial phenomena. Their argument rested not on single observations, but on the cumulative improbability of multiple unusual characteristics appearing together in objects that conventional astrophysics suggested should be common and unremarkable. The statistical analysis began with trajectory precision, computing the probability that two independent interstellar objects would arrive with inclinations matching to 0.02 degrees, velocities differing by less than 2 kilometers per second, and separation distances slowly decreasing over time, yielded combined odds below 1 in 10 million. While not impossible, such probabilities demanded consideration of alternatives to pure chance. Formation flight precision provided the cornerstone of the technological argument. Natural gravitational dynamics don't maintain constant separation distances between unbound objects over millions of kilometers. Yet 4I 2025 U1 maintained position behind 3I Atlas with consistency that suggested active station keeping rather than ballistic coasting. The slight decrease in separation distance could indicate intentional approach rather than gravitational coincidence. The thermal emission patterns drew particular attention from the technological proponents. Natural heat sources like radioactive decay or impact energy dissipate gradually, creating temperature distributions that fade from hot cores toward cooler surfaces. 4I 2025. U1's thermal signature showed temperature concentrations at specific locations rather than smooth gradients, patterns more consistent with localized energy generation than passive cooling. The excess heat persisted across multiple observation epochs without detectable decrease, suggesting ongoing power generation rather than residual warmth. Surface geometry analyses highlighted the polarimetry and radar anomalies as potential manufacturing signatures. Natural weathering processes create random surface features through impacts, thermal cycling, and radiation damage. Finding non-random geometric patterns, preferential orientations, and specular reflections suggested engineered rather than geological origins. The probability calculations for natural processes producing the observed structural correlations came out unfavorably for conventional explanations. The technological framework didn't claim definitive proof. Instead, it argued for hypothesis testing through targeted observations. If 4I 2025 U1 represented artificial construction, it should exhibit characteristics distinguishable from natural objects through sufficiently detailed measurements. Proposed tests included monitoring for trajectory adjustments beyond what outgassing or radiation pressure could produce, searching for non-thermal electromagnetic emissions inconsistent with blackbody radiation, and analyzing surface features for geometric regularities that natural geology doesn't create. The escort behavior itself demanded explanation that the technological proponents argued natural scenarios struggled to provide. Why would a massive inert object follow an active comet through the inner solar system with precision that required either extraordinary coincidence or active control? The configuration resembled what mission planners might design for remote observation or sample collection. One active body releasing volatiles and creating detectable signatures, while a companion maintained nearby positioning for monitoring. Critics within the astronomical community accused the technological proponents of speculation exceeding available evidence, of pattern seeking in noise, of allowing extraordinary possibilities to overshadow mundane explanations. The proponents countered that scientific progress required considering all hypotheses consistent with observations, that dismissing possibilities because they seemed unlikely prevented genuine discovery, that Oumuamua had taught the field to take interstellar object anomalies seriously, rather than forcing them into conventional categories. The debate crystallized fundamental tensions in scientific methodology. How much evidence was sufficient to seriously consider non-natural origins? At what point did statistical improbabilities outweigh preference for conventional explanations? The technological proponents argued that 4I 2025 U1 had already crossed those thresholds, that continued insistence on natural-only interpretations reflected ideology rather than evidence-based reasoning. Between the natural and technological camps, a smaller group of researchers began exploring a hypothesis that seemed even more radical than artificial construction. What if 4I 2025 U1 represented biological material, organic structures evolved or engineered for survival in the extreme environment of interstellar space? The panspermia implications made mainstream scientists uncomfortable, but the chemical signatures kept pointing toward complex carbon-based systems that didn't fit cleanly into either geological or manufactured categories. The biological hypothesis drew support from the object's composition. Polycyclic aromatic hydrocarbons weren't just random organic molecules. They represented building blocks of complex chemistry, compounds that could serve as precursors to more elaborate carbon structures, including those associated with life. The concentration levels detected by James Webb Space Telescope exceeded anything seen in natural space environments, suggesting either unusual formation conditions or active production processes. Extremophile research on Earth demonstrated that life could survive conditions previously thought incompatible with biological processes. Microorganisms thrived in Antarctic ice, deep ocean thermal vents, acidic mine drainage, and even nuclear reactor cooling pools. Tardigrades could survive vacuum exposure and cosmic radiation in laboratory experiments. If terrestrial life showed such resilience under extreme conditions, perhaps organisms adapted to interstellar space weren't as implausible as intuition suggested. The chemical exchange possibility between 3I Atlas and 4I 2025 U1 took on new significance under biological interpretation. If 4I 2025 U1 harbored organic systems capable of processing volatile compounds, the proximity to an actively outgassing comet would provide chemical resources unavailable in the interstellar void. Water vapor, carbon dioxide, and complex organic molecules streaming from 3I Atlas could serve as nutrients or raw materials for metabolic processes. Coordinated behavior between the objects gained potential explanation through biological mechanisms. Chemotaxis, the ability of organisms to move toward or away from chemical gradients, operates across all domains of terrestrial life, from bacteria to complex animals. If 4I 2025 U1 possessed systems capable of sensing and responding to chemical emissions from 3I Atlas, the formation flight precision could reflect biological navigation rather than either natural dynamics or technological control. The thermal signature fit biological interpretation through metabolic heat generation. All terrestrial life produces waste heat as a byproduct of energy processing chemistry. The excess temperature detected in 4I 2025 U1 matched levels consistent with large-scale metabolic activity, assuming biological systems operating at the energy efficiency typical of terrestrial organisms. The localized temperature concentrations could indicate regions of enhanced metabolic processing rather than mechanical power generation. The hypothesis faced immediate skepticism from both astrobiologists and astronomers. Critics argued that biological systems required liquid water for chemistry to operate, that interstellar radiation would destroy organic molecules over million-year timescales, that metabolic processes needed continuous energy input, unavailable during interstellar transit. The biological proponents countered with proposals for dormant states similar to bacterial spores, protective mineral matrices shielding internal organic structures, and metabolic activation triggered by approaching stellar systems. Most controversially, some researchers suggested the possibility of directed panspermia, intentional seeding of stellar systems with biological material. If 4I 2025 U1 represented a biological payload deliberately sent towards stars with planetary systems, its escort behavior with 3I Atlas could indicate programmed targeting rather than random encounter. This interpretation merged biological and technological hypotheses into frameworks that made peer reviewers deeply uncomfortable. The astrobiology community remained divided. Some viewed the biological hypothesis as premature speculation, lacking direct evidence of metabolic activity, reproduction, or other definitive life signatures. Others argued that dismissing the possibility without investigation repeated historical mistakes of assuming Earth-based biochemistry represented universal constraints. The breakthrough. Listen Initiative, humanity's most comprehensive search for extraterrestrial intelligence, redirected its considerable observational resources toward 4I 2025 U1 in early November 2025. The decision came after internal debates weighing the low probability of detecting artificial signals against the unprecedented nature of the target. If even a small chance existed that the object represented technology from another civilization, the potential discovery justified the telescope time investment. Radio observations began at the Green Bank Telescope in West Virginia, the world's largest fully steerable radio dish. The 100-meter diameter antenna pointed toward the calculated position of 4I 2025 U1, its receivers scanning frequencies from 1 to 50 gigahertz. This range encompassed the so-called waterhole between hydrogen and hydroxyl emission lines, frequencies that many scientists consider optimal for interstellar communication due to low natural background noise. The observational strategy focused on detecting narrow-band signals. Radio emissions concentrated at specific frequencies with bandwidths far smaller than natural astrophysical processes typically produce. Natural radio sources like pulsars, quasars, and stellar emissions spread their energy across broad frequency ranges. Artificial transmitters can concentrate power into narrow channels, creating distinctive signatures that stand out against the cosmic radio background. 48 hours of intensive monitoring captured terabytes of data, showing no obvious artificial signals. The radio spectrum around 4I 2025 U1 looked essentially identical to empty interstellar space, devoid of the narrow band emissions, regular pulsations, or modulated patterns that would indicate intentional transmission. Background checks against known satellite frequencies ruled out terrestrial interference masquerading as signals from the target. Optical SETI observations complemented the radio search using visible and near-infrared wavelengths. Laser communications offer advantages over radio for interstellar messaging, concentrating enormous power into tightly focused beams at frequencies that penetrate interstellar dust better than radio waves. The optical SETI instruments searched for brief laser pulses or continuous illumination at wavelengths favored by efficient laser technology. Specialized detectors monitored for nanosecond duration flashes that would indicate pulsed laser communications. Even at interstellar distances, powerful lasers could briefly outshine their parent stars during pulse transmission, creating detectable signatures if aimed toward Earth. The observations captured nothing unusual, just the faint reflected sunlight expected from a dark, distant object with no evidence of artificial illumination. Infrared monitoring searched for excess emission at wavelengths characteristic of waste heat from power generation or propulsion systems. Any sufficiently advanced technology processing significant energy must radiate waste heat according to thermodynamic principles. The infrared signature already detected showed thermal excess, but the spectrum matched heated solid surfaces rather than the specific emission lines that industrial processes or nuclear reactions typically produce. The null results disappointed those hoping for clear evidence of artificial origin, while satisfying skeptics who considered the entire exercise unlikely to succeed. But absence of detected signals didn't prove absence of technology. For I-2025, U1 might not be transmitting. Its systems might operate at frequencies or using modulation schemes that human receivers couldn't recognize. It might be dormant, damaged, or simply not designed for communication with primitive civilizations like humanity. The SETI teams emphasized that their observations sampled only tiny fractions of possible signal space. Radio searches covered limited frequency ranges during brief observation windows. Optical monitoring captured microseconds of potential laser pulse sequences that could span hours or days. Infrared spectroscopy lacked resolution to detect subtle emission features that exotic technologies might produce. The searches ruled out obvious beacons, but left vast parameter space unexplored where more subtle signals could hide undetected. The SETI observations raised an uncomfortable question that quickly escalated into international debate. Should humanity attempt active communication with 4I-2025U1? The proposal divided scientists, policymakers, and the public into camps reflecting fundamentally different assessments of risk versus potential reward. For the first time since the object's discovery, the discussion moved beyond passive observation toward direct interaction. Active messaging to interstellar objects wasn't entirely unprecedented. The Arecibo message transmitted toward Globular Cluster, Messier 13 in 1974, demonstrated technical capability, if not practical communication strategy. More recent proposals for messaging extraterrestrial intelligence had generated controversy within the SETI community, with prominent researchers arguing that broadcasting Earth's presence before understanding who might be listening constituted dangerous naivety. 4I-2025. U1 presented a unique case because the target was already here, already in our solar system, already positioned to observe Earth whether humanity transmitted or remained silent. If the object harbored intelligence or technology, it had already detected our planet's atmospheric signatures, radio leakage, and other techno-signatures that make Earth visible to any civilization with modest observational capabilities. The usual arguments about revealing our location seemed less relevant when the potential observer had already arrived. Proponents argued that transmission represented humanity's best chance to determine the object's nature before it departed beyond effective communication range. A carefully designed message could test for technological presence without revealing sensitive information about human civilization. Basic mathematical concepts, physical constants, and simple information theory principles could establish common ground for mutual understanding while minimizing potential risks. The planetary defense community raised immediate objections. Protocols established through decades of near-Earth object tracking and impact risk assessment emphasized caution when dealing with unknown phenomena. Transmitting to an object whose nature remained uncertain could trigger unintended responses. If 4I-2025U1 represented dormant technology that reacted to specific stimuli, active messaging might constitute exactly such a stimulus. International consultation became legally necessary under the Outer Space Treaty provisions regarding activities that could affect other nations' interests. The United Nations Committee on the Peaceful Uses of Outer Space convened emergency sessions to establish whether active messaging constituted an activity requiring multilateral approval. Member states expressed divergent views reflecting cultural attitudes toward contact with potential non-human intelligence. The technical working group, tasked with message design, faced constraints that made previous interstellar messaging attempts seem straightforward by comparison. The message needed to be detectable by technology, using unknown physical principles, comprehensible to intelligence with unknown cognitive architecture, and transmitted within weeks before the objects moved beyond effective range. The Arecibo message had targeted a stellar cluster that wouldn't receive the transmission for 25,000 years, allowing leisurely design debate. 4 I-2025. U1 demanded decisions on timescales of weeks. Proposed transmission protocols included radio broadcasts at multiple frequencies, optical laser pulses modulated with mathematical sequences, and even intentional satellite maneuvers, creating artificial orbital patterns that might attract attention from observing systems. Each approach carried different risk profiles and detection probabilities that proved difficult to assess objectively. The decision deadline approached as both objects continued their outbound trajectories. Every day of delay reduced signal strength and increased light travel time for potential responses. Mission planners calculated that transmission needed to occur before mid-December 2025 to maintain reasonable probability of detection and response before the objects passed Jupiter orbit and accelerated toward interstellar space. Public opinion polls showed populations divided nearly evenly between those favoring transmission and those preferring continued passive observation. The debate had transcended scientific discussion to become a referendum on humanity's approach toward the unknown. The response came not from 4 I-2025 U1, but from 3 I-Atlas, and it appeared 16 hours after breakthrough. LISTEN completed its intensive SETI observation campaign. The timing could have been coincidence. The astronomical community desperately wanted it to be coincidence. But the precision astrometry measurements that detected the change left little room for comfortable dismissal. 3 I-Atlas exhibited subtle non-gravitational acceleration, a tiny trajectory adjustment measuring just 3/10,000ths of 1 astronomical unit over a 48-hour period. The magnitude was small, barely above detection thresholds, even for the global observatory network's accumulated precision. But the direction was unmistakable. The acceleration vector pointed toward 4 I-2025 U1, reducing the separation distance between the objects by approximately 400,000 kilometers. Non-gravitational accelerations weren't unprecedented in 3 I-Atlas. The object had shown measurable but minimal rocket effects throughout its passage, those tiny pushes from outgassing jets that made its mass estimate so controversial. But previous accelerations had appeared random in direction, varying with solar heating patterns and rotation. This new acceleration showed directionality that seemed purposeful rather than stochastic. The timing troubled researchers more than the acceleration itself. 16 hours represented plausible light travel time for a signal originating near 4 I-2025 U1 to reach 3 I-Atlas and trigger a response. At their current separation of 0.15 astronomical units, roughly 14 million miles, light required approximately 8 minutes for one-way travel. Round-trip communication would take 16 minutes. The 16-hour delay could accommodate signal processing, decision-making, and response implementation by systems operating on timescales vastly slower than human cognition. Skeptics immediately proposed natural explanations. Perhaps 3I Atlas was experiencing an outburst, a sudden increase in volatile sublimation that happened to point jets toward 4I-25 U1 through pure chance. Solar system comets occasionally showed such outbursts, triggered by thermal stress releasing pockets of trapped volatiles. The timing correlation with SETI observations could be purely coincidental, humans pattern-seeking in events that had no causal connection. But detailed analysis of 3I Atlas's activity levels before and after the acceleration showed no evidence of increased outgassing. The carbon dioxide and water vapor production rates, measured by spectroscopic monitoring, remained essentially constant. Whatever produced the acceleration wasn't leaving detectable chemical signatures in the coma. The push appeared mechanical rather than chemical, force without observable propellant. Photometric measurements tracking 3I Atlas's brightness showed subtle modulation patterns that hadn't been present in earlier observations. The variations were small, less than 5% brightness changes over periods of several hours. Natural rotation of an irregularly shaped nucleus could produce such variations, but the previous months of observation had established 3I Atlas's rotation period and light curve. The new modulations didn't match the established pattern. The global observatory network intensified monitoring of both objects, while mission controllers debated whether to continue or suspend SETI observations. If the timing represented genuine correlation rather than coincidence, further transmissions might trigger additional responses that could provide data impossible to obtain through passive observation. But if the acceleration was natural coincidence, continued active messaging represented unnecessary risk based on pattern recognition in noise. Ground-based radar facilities attempted ranging measurements to both objects with increased temporal resolution, hoping to detect any further trajectory changes within hours rather than days. Space-based infrared telescopes maintained continuous monitoring for thermal signature variations that might indicate activation of dormant systems or increased metabolic activity in biological scenarios. The scientific community held its collective breath, uncertain whether they were witnessing the most significant discovery in human history or the most elaborate coincidence in astronomical observation. The answer would come in February, when both objects reached their closest mutual approach, and whatever connection existed between them became impossible to ignore. The response came not from 4I-25 U1, but from 3I Atlas, and it appeared 16 hours after breakthrough. LISTEN completed its intensive SETI observation campaign. The timing could have been coincidence. The astronomical community desperately wanted it to be coincidence. But the precision astrometry measurements that detected the change left little room for comfortable dismissal. 3I Atlas exhibited subtle non-gravitational acceleration, a tiny trajectory adjustment measuring just 3/10,000ths of one astronomical unit over a 48-hour period. The magnitude was small, barely above detection thresholds, even for the global observatory network's accumulated precision. But the direction was unmistakable. The acceleration vector pointed toward 4I-25 U1, reducing the separation distance between the objects by approximately 400,000 kilometers. Non-gravitational accelerations weren't unprecedented in 3I Atlas. The object had shown measurable but minimal rocket effects throughout its passage, those tiny pushes from outgassing jets that made its mass estimate so controversial. But previous accelerations had appeared random in direction, varying with solar heating patterns and rotation. This new acceleration showed directionality that seemed purposeful rather than stochastic. The timing troubled researchers more than the acceleration itself. 16 hours represented plausible light travel time for a signal originating near 4I-2025 U1 to reach 3I Atlas and trigger a response. At their current separation of 0.15 astronomical units, light required approximately 8 minutes for one-way travel. Round-trip communication would take 16 minutes. The 16-hour delay could accommodate signal processing and response implementation. Skeptics immediately proposed natural explanations. Perhaps 3I Atlas was experiencing an outburst, a sudden increase in volatile sublimation that happened to point jets toward 4I-2025 U1 through pure chance. Solar system comets occasionally showed such outbursts triggered by thermal stress releasing trapped volatiles. The timing correlation with SETI observations could be purely coincidental. But detailed analysis of 3I Atlas's activity levels before and after the acceleration showed no evidence of increased outgassing. The carbon dioxide and water vapor production rates measured by spectroscopic monitoring remained essentially constant. Whatever produced, the acceleration wasn't leaving detectable chemical signatures in the coma. The push appeared mechanical rather than chemical, force without observable propellant. Photometric measurements tracking 3I Atlas's brightness showed subtle modulation patterns that hadn't been present in earlier observations. The variations were small, less than 5% brightness changes over periods of several hours. Natural rotation of an irregularly shaped nucleus could produce such variations, but previous months had established 3I Atlas's rotation period and light curve. The new modulations didn't match the established pattern. The global observatory network intensified monitoring of both objects, while mission controllers debated whether to continue or suspend CT observations. If the timing represented genuine correlation, further transmissions might trigger additional responses, providing impossible data through passive observation alone. But if the acceleration was natural coincidence, continued active messaging represented unnecessary risk. Ground-based radar facilities attempted ranging measurements to both objects with increased temporal resolution, hoping to detect further trajectory changes within hours rather than days. Space-based infrared telescopes maintained continuous monitoring for thermal signature variations that might indicate system activation. The scientific community held its breath, uncertain whether they were witnessing the most significant discovery in human history or the most elaborate coincidence in astronomical observation. The answer would come in February, when both objects reached closest mutual approach. The containment collapsed on November 14th, 2025, when leaked Parker Solar Probe images appeared simultaneously on 3 major social media platforms. The images showed both objects in the same frame, their separation distance visible, their trajectories calculable by anyone with basic orbital mechanics software. Within 6 hours, the posts had accumulated over 50 million views and spawned thousands of derivative analyses, ranging from careful scientific interpretation to wild speculation about alien motherships. Space agencies had anticipated eventual leaks, but not the speed or coordination. The simultaneous posting across platforms suggested organized disclosure rather than random security breach. Investigators never identified the source, though suspicions focused on personnel frustrated with the prolonged classification of data. They believed the public deserved to access immediately. The images themselves showed nothing dramatic. Two faint objects against the star field, barely distinguishable from background noise without enhancement. But context transformed mundane pixels into cultural phenomenon. Social media exploded with threads analyzing every aspect of the discovery, amateur astronomers sharing their own observations, and armchair experts proposing theories that ranged from plausible to absurd. Conspiracy frameworks proliferated faster than fact-checking could contain them. Claims that governments were hiding definitive proof of extraterrestrial technology gained traction despite lack of supporting evidence. Assertions that the objects represented existential threats to Earth circulated widely, despite clear orbital calculations showing no collision risk. Narratives about ancient aliens, interdimensional travelers, and time-displaced human technology found eager audiences. Government space agencies scrambled to regain narrative control through official press conferences that emphasized scientific uncertainty and cautioned against premature conclusions. NASA, the European Space Agency, and other national organizations issued carefully worded statements acknowledging the unusual characteristics, while stressing that natural explanations remained viable. The measured tone satisfied no one, appearing evasive to those demanding transparency and insufficiently cautious to those advocating silence until peer review completed. Traditional media outlets struggled to cover a story that evolved faster than publication cycles allowed. By the time news organizations fact-checked claims and conducted expert interviews, social media had moved 3 speculation cycles ahead. The democratization of astronomical data through public archives meant anyone could download images and perform analyses, creating thousands of independent researchers whose conclusions varied wildly in quality and credibility. The United Nations Committee on the Peaceful Uses of Outer Space convened an emergency session to address international concerns about the objects and coordinate response protocols. Member nations expressed frustration that no established framework existed for managing discoveries with potential global implications. The session produced calls for transparency, international cooperation, and accelerated observation campaigns, but no binding decisions about how humanity should proceed. The professional astronomical community, normally united by shared methodology and peer review standards, began splitting into factions that communicated through increasingly hostile exchanges in academic journals and conference presentations. What started as legitimate scientific disagreement about interpretation escalated into something uglier, where career consequences and professional reputations became weapons in debates that transcended mere data analysis. Researchers who publicly supported technological or biological interpretations found themselves facing unexpected obstacles. Grant applications that previously sailed through review processes now received rejections, citing insufficient rigor or speculative methodology. Telescope time proposals for continued observation of the objects faced skeptical evaluation from time allocation committees who questioned whether resources should support investigations of phenomena that might prove mundane upon further study. The peer review process, traditionally anonymous and focused on scientific merit, became weaponized. Papers proposing exotic explanations for the object's characteristics received harsh reviews that went beyond technical criticism into personal attacks on author competence. Reviewers demanded impossible levels of proof for unconventional interpretations, while accepting conventional explanations with minimal supporting evidence. The double standard became obvious enough that several journals faced accusations of editorial bias. Career implications intensified the fracture. Junior researchers found themselves caught between genuine scientific curiosity about the objects and advice from senior colleagues to avoid controversial topics that could derail tenure prospects. Graduate students working on interstellar object research reported pressure to frame their analyses within strictly natural explanations, regardless of what data suggested. The chilling effect on open scientific inquiry became impossible to ignore. Funding agencies contributed to the problem through risk-averse allocation decisions. Proposals for missions or observations that might detect definitive evidence of non-natural origins faced skepticism about return on investment. Why commit resources to investigations that probably would find nothing unusual when those same resources could support research into well-established phenomena? The logic was sound financially, but potentially catastrophic scientifically, if it prevented detection of genuinely unprecedented discoveries. Social media amplified the professional divisions by making internal scientific debates visible to public audiences unfamiliar with how research communities normally operate. Disagreements that would traditionally play out over years through published papers and conference discussions now occurred in real time on platforms where context collapsed and nuance disappeared. Scientists found their careful qualifications stripped away, their positions caricatured by both supporters and opponents. Historical parallels to the continental drift controversy emerged in discussions about scientific sociology. When Alfred Wegener proposed that continents moved, the establishment dismissed the idea for decades, despite mounting evidence, protecting conventional frameworks, until the weight of observation forced paradigm shift. Some researchers worried that similar dynamics were preventing objective evaluation of what 4 I-2025, U-1, and 3 I-Atlas actually represented. The democratization of astronomy accelerated dramatically as crowdfunding campaigns raised millions of dollars for independent observation time at private telescope facilities. Public frustration with institutional caution and perceived scientific gatekeeping translated into direct action, with citizen groups purchasing their own access to professional-grade instruments and conducting observations free from academic politics or government oversight. Amateur astronomer networks coordinated global coverage that rivaled official observation campaigns in temporal density, if not individual measurement precision. Thousands of backyard telescopes across 6 continents pointed toward the objects whenever darkness and weather permitted, uploading images and photometric data to public repositories within hours of collection. The distributed network provided continuous monitoring that no single institution could match. Citizen science projects emerged to analyze the flood of public data. Volunteers with backgrounds in statistics, image processing, and data science contributed expertise to collaborative platforms where anyone could download raw observations and perform independent analyses. Some projects focused on trajectory refinement, using thousands of astrometric measurements. Others attempted spectroscopic analysis by combining multiple amateur observations to achieve signal-to-noise ratios approaching professional facilities. the quality varied enormously. Sophisticated amateur groups with access to university surplus equipment produced data rivaling professional observatories. Others contributed measurements plagued by systematic errors from inadequate calibration or atmospheric effects. But the sheer volume compensated for individual quality issues, allowing statistical techniques to extract reliable signals from noisy datasets. Social media coordination proved surprisingly effective at directing observational resources towards specific scientific questions. When professional astronomers published papers identifying gaps in temporal coverage or wavelength ranges, amateur networks responded within days with targeted observation campaigns. The traditional distinction between professional and amateur astronomy blurred as collaboration replaced the historical one-way flow of information from institutions to public. Private space companies offered their own contributions. Several firms with launch capabilities proposed rapid response missions using existing spacecraft designs adapted for interstellar object investigation. The proposals emphasized speed over sophistication, arguing that even crude flyby observations would exceed anything ground-based telescopes could provide. Cost estimates ranged from $200 million to over $1 billion, depending on payload complexity and trajectory requirements. Crowdfunding for actual space missions proved more challenging than telescope time purchases. Despite viral social media campaigns and celebrity endorsements, public contributions plateaued around $50 million, far short of minimum mission costs. The gap between public enthusiasm and financial reality demonstrated limits to citizen-funded space exploration, though several private companies indicated willingness to absorb cost differences in exchange for mission naming rights and data access. The public pressure campaign succeeded in forcing transparency from institutions that preferred classified analysis. Space agencies found themselves releasing preliminary data earlier than traditional scientific caution recommended, responding to demands for information from populations unwilling to wait for peer review completion. The original plan to redirect Juno spacecraft toward 3I Atlas became obsolete the moment Parker Solar Probe detected 4I 2025 U1. Mission planners faced an excruciating choice between two unprecedented targets, both approaching Jupiter on trajectories that would allow close encounters, but not both simultaneously. The spacecraft carried enough fuel for one major trajectory change, not two. Congressional hearings on mission priority revealed deep divisions about which object deserved humanity's first close-up investigation. 3I Atlas offered the familiar, an active comet with measurable outgassing and chemistry accessible to existing instruments. Scientists understood comets. Juno's magnetometer and infrared spectrometer could characterize 3I Atlas using proven techniques refined through decades of solar system exploration. 4I 2025. U1 represented the unknown, its dark surface, thermal anomalies, and potential connection to 3I Atlas made it scientifically compelling but operationally risky. Juno's instruments were designed for Jupiter's magnetosphere and radiation environment, not characterizing potentially manufactured or biological materials. The spacecraft might fly by 4I 2025 U1 and return data that raised more questions than answers. Fuel calculations constrained the decision timeline. Every week of delay reduced maneuver efficiency as both targets moved along their trajectories. Mission controllers calculated that commitment needed to happen by mid-December 2025 to maintain reasonable intercept probabilities for either object during the March 2026 Jupiter encounter window. The debate extended beyond pure science into philosophy about exploration priorities. Should humanity investigate the explicable or the inexplicable first? Did the potential for revolutionary discovery outweigh the certainty of advancing comet science through 3I Atlas observations? The questions had no objective answers, only values, judgments about acceptable risk versus reward. Technical working groups modelled hybrid scenarios where Juno performed distant observations of one target while passing close to the other. The compromises satisfied no one, offering reduced science return from both objects, while consuming fuel that might be needed for trajectory corrections. The mission team eventually concluded that trying to observe both targets meant getting poor data from each rather than excellent data from one. The European Space Agency proposed what mission designers called the fastest deep space response in human history. A rapid deployment spacecraft carrying minimal instrumentation could launch in December 2025 and reach intercept trajectory by May 2026 if everything went perfectly. The mission would cost approximately $800 million minimum, require international partnership, and push engineering timelines to breaking points. The spacecraft design emphasized speed over sophistication. A simple camera system for imaging, a basic spectrometer for composition analysis, and a magnetometer for detecting magnetic fields represented the entire science payload. No sample return capability, no advanced instruments requiring years of development, just proven hardware adapted from existing missions and assembled in weeks rather than years. Launch vehicle selection focused on availability rather than optimization. Several rockets capable of achieving the necessary trajectory sat in various stages of preparation at launch facilities worldwide. The proposal identified 3 potential boosters that could be repurposed with minimal modification, though each came with schedule risks and contractual complications from displacing previously manifested payloads. Trajectory calculations revealed the tight constraints. The spacecraft would need to achieve Earth escape velocity, perform a carefully timed burn near Mars orbit for gravitational assist, then intercept 4I-2025U1 as both spacecraft and target converged near Jupiter's orbit. Miss any of these milestones by even small margins and the mission would fail completely. The spacecraft sailing past its target with cameras pointed at empty space. International coalition building began immediately. NASA contributed deep space communication infrastructure and mission operations expertise. The Japan Aerospace Exploration Agency offered trajectory analysis and backup communication assets. Russia's space agency provided potential launch vehicles and tracking support. China announced an independent but parallel mission concept, using their own launch systems and spacecraft design. The aggressive timeline terrified risk-averse program managers, while exciting engineers who relished technical challenges. 6 weeks for final design, 8 weeks for assembly and testing, 2 weeks for launch preparation. Every phase compressed to minimum durations, with no margin for unexpected problems. One significant delay anywhere in the chain would push launch past the optimal window and dramatically reduce intercept probability. The emergency mission transformed from European proposal to genuine international coalition within 3 weeks of initial announcement. NASA committed $500 million in funding along with deep space network tracking time and mission operations expertise. The European Space Agency provided spacecraft bus design and assembly facilities at their technical center in the Netherlands. Japan offered trajectory optimization algorithms and backup communication assets through their global antenna network. Russia's participation proved more complicated due to ongoing geopolitical tensions unrelated to space exploration. Roscosmos initially offered Soyuz launch vehicles and tracking station access, then withdrew under political pressure before eventually rejoining with reduced but meaningful contributions. The participation fluctuations delayed schedule planning and forced backup arrangements that added program costs. China's announcement of an independent parallel mission created both competition and opportunity. The Chinese National Space Administration revealed plans for their own intercept spacecraft launching in late December 2025 on a Long March 5 rocket. The trajectory differed from the international mission, targeting earlier intercept in April 2026 with lower flyby velocity but reduced observation time. Having two spacecraft approaching from different directions could provide stereoscopic observations impossible with single mission architecture. Private space companies volunteered launch services at reduced commercial rates, recognizing the public relations value of participating in potentially historic missions. SpaceX offered Falcon heavy launch capability. United Launch Alliance proposed using Atlas V with extended fairing. Several smaller companies suggested their developing heavy lift vehicles might reach operational status within the required timeline, though mission planners dismissed these proposals as unrealistic given untested hardware. First contact protocols became contentious negotiation points. If either spacecraft detected evidence of technology or biology, which nation had authority to make public announcements? What communication procedures would govern information sharing between missions? How would sample priorities be established if return capabilities were added to mission designs? These questions revealed underlying tensions about scientific leadership and discovery rights that transcended pure technical cooperation. The coalition agreements eventually established joint mission operations centers with shared real-time data access and coordinated decision-making authority. No single nation would control observations or announcement timing. The framework represented unprecedented international cooperation driven by recognition that the targets transcended national interests. February 14th, 2026 arrived with global observation networks operating at maximum capacity. 3I Atlas and 4I 2025. U1 reached minimum separation of 0.08 astronomical units, roughly 12 million kilometers, the closest they would approach during their entire passage through the solar system. Every major telescope on Earth and in orbit pointed toward the convergence zone, capturing data across wavelengths from radio to gamma rays. The objects maintained their formation with precision that continued defying natural explanations. Trajectory updates based on thousands of positional measurements showed both following paths that would keep them separated by nearly constant distance, even as Jupiter's gravity began influencing their orbits. The coordination persisted through gravitational perturbations that should have altered their relative positions if they were truly independent bodies on ballistic trajectories. Spectroscopic monitoring of 3I Atlas showed activity levels remaining essentially constant despite approaching the convergence point. Water vapor and carbon dioxide production rates matched predictions based on solar heating at current heliocentric distance. No outbursts, no unusual jets, no chemical signatures suggesting interaction with its companion beyond the subtle trajectory adjustment detected in November. 4I 2025. U1 maintained its spectral silence. Multiple observatories attempted detecting any emission features that might indicate activation or response to proximity with 3I Atlas. The searches found nothing, just the same dark surface absorbing sunlight and radiating thermal excess without revealing composition through characteristic spectral signatures. Then, 47 hours after closest approach, something changed. Infrared monitoring detected brightness variations in 4I 2025 U1 that exceeded normal measurement noise. The changes weren't dramatic, perhaps 10% fluctuation in thermal emission over 6-hour periods. But the timing and pattern suggested something was happening inside or on the surface of the larger object. Ground-based radar facilities increased observation cadence to hourly intervals. The returns showed surface characteristics remaining essentially unchanged, but polarization measurements detected subtle shifts consistent with material redistribution or activation of previously dormant surface features. Something about the close approach had triggered response in the silent companion, and astronomers worldwide scrambled to understand what they were witnessing as both objects continued their coordinated journey toward Jupiter. What happened in the 72 hours following the February convergence forced even the most skeptical astronomers to acknowledge they were observing something beyond conventional physics. Both objects exhibited simultaneous trajectory adjustments, detectable by multiple independent observation networks. The changes weren't subtle artifacts requiring statistical analysis to extract from noise. They were clear, coordinated, and physically significant. 3I Atlas showed non-gravitational acceleration, measuring approximately 0.005 astronomical units per day squared, roughly 5 times larger than any previous deviation from gravitational trajectory. The acceleration vector again pointed toward 4I 2025 U1, continuing the approach pattern initiated in November, but with dramatically increased magnitude. Outgassing observations showed no corresponding increase in volatile production that could explain the enhanced thrust through natural rocket effects. 4I 2025 U1, previously following a purely gravitational path, exhibited its first detectable non-gravitational acceleration since discovery. The magnitude matched 3I Atlas within measurement uncertainty. The direction pointed back toward its companion. Both objects were adjusting trajectories to reduce separation distance through forces that left no obvious chemical signatures. The synchronization extended beyond direction to timing. Analysis of high-cadence astrometric measurements showed the accelerations beginning within 2 hours of each other across 14 million kilometers of separation. Light travel time at that distance was roughly 1 minute. Whatever coordination mechanism operated between the objects, it responded far faster than chemical processes could explain, but potentially consistent with electromagnetic signaling. Orbital mechanics calculations projected new trajectories converging within 90 to 120 days. If both objects maintained current acceleration profiles, they would reach physical proximity sometime in late May or early June 2026. The separation distance would drop from millions of kilometers to potentially thousands or less, close enough for gravitational interaction, possible collision, or whatever other interaction their coordinated behavior was designed to achieve. Spectroscopic monitoring intensified as astronomers searched desperately for chemical explanations that could preserve natural interpretations. The observations found nothing. Both objects continued exhibiting coordinated thrust without detectable propellant, momentum transfer without visible mechanism, synchronized behavior that seemed to mock conventional physics while operating within its mathematical framework through means that remained completely mysterious. The transformation began on February 19th, 2026, 6 days after closest approach, 4I-2025. U1, the silent dark companion that had shown no volatile activity throughout months of observation, suddenly developed a faint coma visible in deep exposures from ground-based telescopes. The appearance wasn't gradual warming, triggering slow sublimation. It was abrupt activation, 0 to detectable in less than 24 hours. Initial reports came from amateur astronomers conducting routine photometric monitoring. Professional facilities confirmed the changes within hours, their larger apertures and sensitive detectors revealing not just brightness increase, but actual coma structure, fuzzy extended emission surrounding the previously point-like nucleus. Spectroscopic analysis of the new coma showed composition that made no sense given 4I-2025 U1's previous inert behavior. Water vapor emissions appeared at wavelengths matching 3I Atlas's signature. Carbon dioxide bands showed intensity ratios nearly identical to measurements from the active companion. The chemistry wasn't just similar, it was essentially indistinguishable within observational uncertainties. This matching composition created immediate theoretical problems. If 4I-2025 U1 contained volatile ices similar to 3I Atlas, why had it remained completely inactive for months, while its companion actively sublimated? Finding 4I-2025 U1 suddenly producing exactly the same chemical signatures as 3I Atlas suggested something other than natural thermal response. The brightness increase measured 2.5 magnitudes over 48 hours, making the object roughly 10 times brighter than its previous dark appearance. Within 10 days, 4I-2025 U1 had transformed from barely detectable dark object into visually prominent comet, rivaling 3I Atlas in apparent brightness, despite remaining more distant from both Sun and Earth. Coma morphology analysis revealed structures that deepened the mystery. The expanding gas and dust didn't spread uniformly in all directions, as thermal sublimation would produce. Instead, the emission showed directionality, material flowing preferentially toward 3I Atlas. High-resolution imaging detected what appeared to be a focused jet or stream connecting the two objects across millions of kilometers, a bridge of gas and dust spanning the void between them. Material transfer between objects separated by such distances violated intuitive expectations about how comets behave. Gas molecules escaping from a sublimating surface typically expand radially outward at hundreds of meters per second, quickly dispersing into the vacuum of space. Finding collimated flow, maintaining coherence across millions of kilometers, suggested either exotic physics governing the gas dynamics or active focusing mechanisms directing material flow. James Webb Space Telescope observations detected the bridge structure in infrared wavelengths, confirming it wasn't an optical illusion or image processing artifact. The emission showed temperature and density gradients consistent with material flowing from 4I-2025 U1 toward 3I Atlas, though the mechanisms producing such focused transport remained completely unexplained. The precision of trajectory matching between 3I Atlas and 4I 2025 U1 had exceeded natural gravitational dynamics since discovery, but the synchronized accelerations detected in February elevated the formation flight from statistical anomaly to physical impossibility within conventional frameworks. Multiple research teams published detailed analyses attempting to quantify exactly how improbable the observed coordination was, and the numbers they calculated left little room for comfortable interpretation. The February adjustments showed both objects changing velocities by nearly identical amounts within 2-hour timing windows across 14 million kilometer separation. The probability of such coordination occurring through independent random processes calculated to less than 1 in 10 billion. Even allowing generous uncertainties in acceleration measurements and timing precision, the statistics remained overwhelmingly against coincidence. Gravitational physics offered no mechanism for maintaining the observed formation flight. The objects weren't orbiting each other. Their mutual gravitational attraction at current separation was negligible compared to solar gravity. Either controlled propulsion or unknown physics represented the only remaining explanations that fit observations. The academic papers analyzing formation flight carefully avoided definitive conclusions while making the constraints clear. Natural processes couldn't maintain such precise coordination over millions of kilometers. The observations demanded explanation beyond conventional comet dynamics. Whatever was happening, it represented either engineering or physics that human science had not previously encountered. The formation flight analysis marked a turning point in scientific discourse about the objects. Mainstream astronomy could no longer dismiss exotic interpretations as premature speculation. The data now demanded serious consideration of possibilities that would have seemed absurd months earlier. The biological interpretation gained unexpected support from the chemical exchange observations. Material flowing from 4I 2025 U1 toward 3I Atlas suggested interaction patterns more consistent with biological systems than geological processes or mechanical technology. The chemistry showed complexity that simple volatile sublimation couldn't easily explain. Terrestrial biology demonstrated that organisms could coordinate behavior across distances through chemical signaling. Ant colonies communicated via pheromone trails. Bacterial populations achieved quorum sensing through molecular exchange. If biology could produce such coordination at microscopic scales, perhaps analogous processes operated at astronomical scales for organisms adapted to interstellar environments. The material bridge connecting the objects took on new significance under biological interpretation. Rather than random gas dispersion, the focused flow could represent intentional chemical transport. The synchronized trajectory adjustments could reflect chemotaxis operating across millions of kilometers. Metabolic heat generation explained the thermal excess detected in both objects. All terrestrial life produces waste heat through energy processing. The temperature patterns observed, particularly the localized concentrations, rather than uniform gradients, resembled biological heat signatures more than geological or mechanical sources. Both objects continued their outbound journey toward Jupiter as humanity scrambled to launch missions that might reach them before they accelerated toward interstellar space. The International Coalition spacecraft remained in final assembly, its December 2025 launch date already missed due to technical delays. The revised schedule targeted late March 2026, cutting intercept margins to uncomfortable minimums. China's independent mission launched on February 28th from Wenchang Space Launch Site. The Long March 5 rocket performed flawlessly, placing the spacecraft on trajectory for April intercept with 4 I-2025-U1. The emergency missions represented humanity's best chance to answer questions that passive observation couldn't resolve. Close-up imaging could detect surface features indicating manufacturing or biological structures. Composition analysis might reveal organic polymers or unusual isotope ratios. But even if missions succeeded, they would arrive during the most critical phase, when both objects approached potential contact. The story of 3I Atlas and 4I 2025 U1 reaches no conclusion because their journey continues. As this account closes in early March 2026, both objects accelerate toward Jupiter, while humanity watches with instruments, spacecraft, and growing understanding that the universe operates through processes we have barely begun to comprehend. The questions multiply faster than answers emerge. Are we observing natural phenomena that simply exceed current theoretical frameworks? Do the objects represent technology from civilizations whose capabilities dwarf our own? Could biology adapt to interstellar space in ways terrestrial evolution never explored? Each possibility seems equally improbable, yet equally consistent with accumulated observations that refuse conventional categorization. The emergency missions launching in coming weeks will provide data impossible to obtain through ground-based telescopes. But even definitive answers about these specific objects leave broader questions unresolved about what else travels through the space between stars. The Vera Rubin Observatory begins full operations in 2027, scanning the southern sky with capabilities that will discover dozens or hundreds of interstellar visitors annually. If 3I Atlas and 4I 2025 U1 represent typical travelers, the coming decade will revolutionize understanding of galactic material exchange. The silent giants carry secrets that may remain partially hidden even after spacecraft encounters and years of continued observation. Their coordinated dance through our solar system has already transformed interstellar object astronomy from curiosity-driven investigation into urgent exploration of phenomena that challenge fundamental assumptions about what exists in the universe. What emerges when they finally converge near Jupiter in May will either answer the questions that have consumed scientific discourse for months, or generate entirely new mysteries that will haunt astronomy for generations. Either outcome represents discovery, the recognition that reality exceeds imagination and nature operates through mechanisms awaiting patient observation and humble inquiry.